Last episode, we caught ransomware beacons hiding in 1.5% of traffic. Scale pose weight tilted the gradient back toward the rare class, and recall jumped. But beacons are a needle. Today, the haystack fights back. We're running an intrusion detector over raw net flow records, DOS floods, port scans, exfil tunnels, all mixed into normal traffic. 14 flow features, 18,000 connections, a quarter of them hostile. Flow data is noisy, 2 scans never look quite the same, and a deep enough tree will happily memorize the noise and call it a signature. So this episode isn't about a new trick. It's about the 4 knobs that decide whether XGBoost learns the attack or learns the dataset, and the one chart that tells you which one happened. Here's the misconception that ships broken IDS models. Deeper trees catch more attacks. Crank max depth until recall stops climbing. Watch what actually happens. At depth 6, the validation log loss bottoms at 0.087, pushed to depth 12, and the training log loss collapses towards 0.005. The model is nailing every training flow. But validation log loss rises past 0.15. The deep tree didn't learn more attacks. It learned the training set's attacks down to the per flow jitter and got worse at the ones it hadn't seen. Depth is capacity, and capacity past the signal is just a memorized noise table. So how do you see memorization before it ships? You don't trust one number, you watch 2 curves diverge. XGBoost hands you eval's result. The log loss on train and on a held out validation flow, logged at every boosting round, plot both. The training curve always slides down, more rounds, more memory. The validation curve is the honest one. It drops, bottoms out, then starts creeping back up. The gap between them at the bottom is your overfit gauge. A hair's gap means you're generalizing. A chasm means you've memorized. The misconception killed here is low training loss means a good model. A training log loss near 0.02 is meaningless until you see the validation curve sitting at 0.087 right beside it. Next knob, eta, the learning rate, and the trap is big steps trained faster, so use them. Each boosting round adds one tree scaled by eta. At eta, so on 0.5, the model lurches. It overcorrects on the loud flows, the validation curve gets jagged, and it overfits in 40 rounds. At eta but 0.1, each tree nudges gently. The ensemble averages out the flow noise over hundreds of rounds, and the validation floor drops to zone bores 87. Small steps don't train slower in any way that matters. They train smoother, and smooth is what survives noise. The price is more rounds, which is exactly why the next 2 knobs exist. Subsample and cold sample by tree. The misconception is show every tree all the data and all the features, or you're throwing away signal. The opposite is true on noisy telemetry. Subsample 0.8 means each tree sees a random 80% of the flows. Cold sample by tree 0.8 means each tree sees a random 80% of the features. No single tree can lock onto one flow's quirk because it probably didn't see that flow. The randomness is the regularizer. It forces trees to find signal that's stable across resamples, which is the definition of signal that generalizes. Drop both to 0.8 and the train val gap shrinks without touching depth. Now the misconception that wastes the most compute. More boosting rounds is always safer. Train 1,000 and you can't lose. You can, and the validation curve shows you exactly where. With eval set watching the held out flows, XGBoost tracks val log loss every round. It bottoms at round 227, then climbs. Every round after 227 is the model memorizing harder and generalizing worse. Early stopping rounds, 40 watches for that. 40 rounds with no validation improvement and it halts. Then best iteration rolls the prediction back to round 227. Round 1,000 wouldn't be safer, it'd be strictly worse and slower. So what does the tuned model buy us in SOC terms? Not accuracy. We learned in EPS 04 accuracy lies. On this 25% attack flow set, PR IOC lands at 0.983 and at a strict 0.9% false positive rate. The budget and analyst team can actually triage. Recall is 0.92. That means at depth 6, ATI 0.1, both subsamples at 0.8, stopped at around 227. The detector catches 92 out of every 100 intrusions, while flagging fewer than one normal flow in 100. Push depth to 12, chasing a prettier training loss, and that recall falls because the memorized model is confidently wrong on the flows it's never seen. Here's the whole lesson in one frame. The four knobs aren't independent dials you maximize one at a time. They're a single budget for how much the model is allowed to memorize. Shallow depth, small ATA, subsampled rows and columns. Each one spends a little capacity on staying general, and the learning curve is the receipt. Train curve heading to 0, validation curve bottoming and lifting, the gap at the bottom telling you the truth. A shallow generalizer beats a deep memorizer on flow noise every single time, and the chart proves it before you ever ship. Open 06 netflow IDS.py. It builds the seeded netflow world, fits one XGBoost classifier with the 4 tuned knobs and an eval set, pulls the per round log loss out of eval result, and renders the one figure this episode lives on, the train where's validation learning curve. Everything prints the same numbers the chart draws. First, the seeded flow table. Make classification builds 18,000 connections, 14 features, 10 of them informative, weighted 75-25, benign to attack with class, sep1 do zo zo, and random state the 5, separable enough to be real, noisy enough to punish a memorizer. Then we rename the columns to what a flow record actually carries: duration, bytes in, bytes out, PKTs, sin ratio, fin ratio, DST port entropy, flow IAT mean, and the rest. Same array a Kaggle download would give you, except it reproduces byte for byte in Colab with no download. Next, the split, a stratified 75-25 train validation cut, also seeded. Stratify matters. It keeps the 25% attack ratio identical in both halves, so the validation log loss is measured on the same class balance the model trained on. This validation set is the only thing standing between us and self-deception. Every honest number in this episode comes from it. The model, XGB classifier with the 4 knobs the whole episode is about. Max depth 6, learning rate do 0.1, that's ETA, subsample 0.8, call sample by tree bow 0.8, plus eval metric goes log loss, and early stopping rounds scores of 40. We hand fit an eval set containing both curves, XTR, YTR, XVol, IVol. That's what makes the learning curve possible. XGBoost will now log loss on train and validation at every single round. Now we read the receipt. CLF on eval's result returns a dict. Validation 0 is the train curve. Validation 1 is the validation curve, each a list of log loss per round. We grab best iteration, round 227, where validation bottomed, and print the train and val log loss at that round, 0.016 and 0.087. The gap between them, 0.071, is the overfit gauge in a single number. Finally, the SOC honest metrics and the figure. We score the validation flows, compute PR AUC 0.983, sweep the ROC to find recall at a 0.9% false positive rate, 0.92, and print the headline line. Then we plot both log loss curves over rounds, train in safe green, validation in threat red, and drop an amber vertical rule at round 227 where early stopping fired. Figure, terminal, and headline are the same 5 numbers. So the 4 knobs are a memorization budget, and the learning curve is how you audit it. Shallow and slow beats deep and greedy on flow noise, and you can prove it before deployment. But we've been staring at a score, 0.92 recall at a 0.9% FPR. Next episode we change targets, a back and spam filter, where someone to be safe set boosting rounds to 2000. SECU7 shows why more rounds is always better, is the most expensive myth in boosting, and how early stopping rounds, the knob we just leaned on, halts the model the instant the validation curve turns against you.